Hi. So this mini lecture focuses on elimination reactions. So in an elimination reaction, basically a strong base removes a proton from an alkyl halide and it will form an alkene. Alkene, carbon-carbon double bond. So now with a strong base, the elimination process will occur in a concerted manner, kind of like how an SN2 substitution also happens. All the steps of an SN2 reaction also happen all at once. Right? So such a concerted elimination process is called an E2 elimination. So where does the acronym E2 come from? So the E simply stands for elimination, and the 2 is there because the process is bimolecular. So recall that bimolecular means that 2 different reagents need to collide with each other in the transition state during for the slowest step of the reaction. Right? So the concentration of both reagents, in this case the base and the alkyl halide, are both affecting the speed of the reaction. Right? That's where the 2 comes from bimolecular. So here's the mechanism of an E2 elimination. Essentially, we have the process first involves a proton transfer, which happens at the same time as the loss of the leaving group X, right? X recalls the alkyl halide, chlorine, bromine, or iodine. Remember that fluoride, F-, is not a good leaving group, so we wouldn't want to be using it for these processes. So now when the elimination reaction is complete, we form an alkene, the protonated base, and X-. You see, the reason it's called elimination is because we basically eliminated part of the molecule. We took one molecule and split it up into 2. So we eliminated basically XH molecule. Now next, let's talk about how the substrate, so the alkyl halide, affects whether an elimination or a substitution reaction will occur. First, let's recall that a typical anion, right, like hydroxide, can both act as either a strong nucleophile or as a strong base. Right? It's basic and nucleophilic. And therefore, it can participate in nucleophilic, like SN2 substitution reactions, as well as in E2 reactions, right? The question is, when does it do what? So now, as we'll see that for a sterically hindered substrate, E2 elimination becomes greatly favored over SN2 substitution. And so, to understand why this is the case, let's look at an example. Substitution first, right? So we'll have a hydroxide. Assume that we have a hydroxide anion reacting with a tertiary alkyl halide. And so as we have seen, in the prior lectures, such a tertiary substrate is very sterically hindered. And so the hydroxide anion really can't reach the backside of the carbon-halogen bond, right? At this point, also recall that we have seen that all SN2 reactions always need to happen with backside attack, right? So the key thing to remember here is that whenever a substrate is sterically hindered, nucleophilic attack, SN2 reaction, can't happen, and then E2 reaction happens instead. Now let's see how the E2 process takes place. So again, we have our hydroxide and our tertiary substrate. Now in the case of the elimination, the key is to note that for the elimination to happen, the hydroxide anion only needs to be able to reach the hydrogen, one of those hydrogens which are more on the surface of the molecule. Right? These hydrogens are much less occluded than the alpha carbon, which is basically where the substitution would need to occur. So they're more on the surface, and that's why the reaction elimination can readily take place, even though it's a tertiary substrate.